Hi guys, we're back for 1.4 parametric equations. Our objective today is to be able to use parametric equations to obtain graphs of relations and functions. Exciting, I know. Okay, a relation is a set of ordered pairs x, y of real numbers. The graph for the relation is the set of all points in the plane that correspond to ordered pairs in the relation, and if x and y are functions in the third variable t, called a parameter, we use the parameter mode on our calculator. So remember, we can go do that by switching modes. You hit mode and then you just go down and then switch it to parametric. So here we are on example 1. Okay, so describe the graph of the relation determined by x equals the square root of t and then y equals t, where t is greater than or equal to 0. Indicate the direction in which the curve is traced. Find the Cartesian equation for the curve that contains the parameterized curve. Okay, so we're going to begin by, I always just like to rewrite my equations so I have them easy for me to see. X equals square root of t, y equals t, where t is greater than or equal to 0. I'm going to start by looking at my graph. So I'm going to switch the mode on my calculator if you guys haven't already done so. And then I'm going to then put these in. So the square root of x, which then would put it in as t. And then y1 will just be t. Put it on my graph. Okay, so when I put this in the calculator, I'm going to get a rough graph that looks like somewhere in there. So I have that. And then we can go through and then find the Cartesian coordinate equation. We could find this graph, and the way we do that is, if we were going to do it by hand, would be creating that t, x, y chart. So you then have their values of t. So since it's a square root, I would do like 0, 1, 9, let's do 4 and then 9, 4 and 9. And then I could then substitute it in for my x equation, 0, 1, 2, 3, and then my y would just be 0, 1, 4, 9, and then that's what we'd have here. So 1, and then when x is 4, so you know this is not drawn accurately, we'll call that one 4, and then when x is, oh yeah, I was supposed to be 1, 2. So my rough sketch, I will update a little bit. So when x is 2, y is 4. And then when x is 3, y is 9. Okay. Okay, so that's going to be more like our actual graph. And then we want to find the Cartesian equation for the graph that contains this curve. So we want to start with that y equals t, because we know our equation is going to be y something, and then we want to then work with the x. So if I take that x equation, I wish I had a little more space if I would have written that down a little bit further. I want to solve this one. Let's go over here, x square root, x equals the square root of t. I want to get t by itself, so I'm going to square both sides. T equals x squared. So now back over on this side, I have y equals t. Well, now by solving this equation, we know that t equals x squared. So our equation will be y equals x squared in the Cartesian coordinate plane. And this applies for when x is greater than or equal to 0. Okay, so now to determine where the direction of the curve, we look at what our starting point is. Our starting point is going to be where t equals 0, and then it gets greater from there. So you substitute 0 in. So x equals the square root of 0, which is 0. Y equals 0. We see that's 0.00, which is our origin. That means it's going to move going away from there. So that is the direction of our curve. Parametric curves are parametric equations. If x and y are given as functions, x equals f of t and y equals g of t, overall an interval of t values then the set of points x, y equals f of t, g of t, defined by these equations as a parametric curve. The equations are parametric equations for the curve. So we're on our next example, and I have a lot of words here, so not a lot of working out space for me, but I will work on that. So describe the graph of the relation determined by x equals 2 cosine t, y equals 2 sine t, where t is between 0 and 2 pi. Find the initial and terminal points if and we're just going to go with what I was trying to say. Initial and terminal points and indicate the direction the curve is traced. Find the Cartesian equation for the curve that contains the parameterized curve. Okay, sorry about that. I'll fix that grammar in my slides here in a minute, even though that won't help us. So there's a couple different ways of doing this, but what I'm going to start with is we're going to look at our 2. You know I like to write out my stuff first. X equals 2 cosine, ooh, that looks rough. Okay, let's try it again. 2 cosine x t. Sorry guys, I'm getting a lot of messages from people in my geometry classes right now. Y equals 2 sine t. Dropped off that 2 up here. Okay, and we have it for 0 to 2 pi. Okay, so when we're doing this, a nice way of beginning is looking at our x. So we're going to take our x and we're going to try to get that cosine, so the part that has the t by itself. So I'm going to divide over by 2, and I get 2x over 2 cosine of t. Cosine, not cotangent, cosine of t. And then I can create a triangle. You guys might remember this from before. Put your little t in there. And then cosine is adjacent over hypotenuse. We can solve for the other side using Pythagorean Theorem. So that gives me 4 minus x squared. Okay, so then I can now go to my y. Y equals 2 times my sine value, with sine's opposite. So square root of 4 minus x squared over 2. Okay. Let me close my parentheses. And then we're going to go here. We see that our 2's go away. We end up with y equals the square root of 4 minus x squared. Let's get rid of that square root. So we're going to square both sides. We end up with y squared equals 4 minus x squared. Add x squared to both sides. So we end up with the equation of a circle with radius 2. So we can go ahead and graph that. Okay, a little rough, but hopefully yours looks a little bit better. Again, we could have done this by going through points, doing that t, x, y table, but this allowed us to put into an equation the Cartesian coordinate plane that we know and know how to graph. And so by doing this, we can now look and start to see what our values of the initial point are. So to find our initial point, we're going to substitute in 0 into our 2 original equations. So we have x equals, and then it's going to be 2 cosine of 0. And then we have y equals 2 sine of 0. So we know on our unit circle that would be the spot that's 1, 0. So chicken strips, so that means that this is going to be 2, and this one's going to be 0. So it starts at 2, 0. So I can get rid of that. That was just a nice reminder from last year's unit circle. Okay, and we know it goes around the circle to get to 2. Let me find that. 2 pi. So we know our starting point, and then now we have to get to 2 pi from there. So we know we're going to be going counterclockwise around our circle. Okay, graph of 3, or number 3. Graph the parametric curve x equals 3 cosine t, y equals 4 sine t, for 0 is less than or equal to t, less than or equal to 2 pi. Find the Cartesian equation for the curve that contains the parametric curve. What portion of the graph of the Cartesian equation is traced by the parametric curve? Indicate the direction in which the curve is traced and the initial and terminal point. There's a lot of stuff happening. Okay. So here, we're back to x equals 3 cosine t, y equals 4 sine t. Okay, I'm going to rearrange this to try to get the t part by itself. So I end up with cosine t equals x over 3. You can create that triangle t adjacent over hypotenuse. That makes this side 9 minus x squared by the Pythagorean Theorem. So we can go here. Let me change my color so we can distinction between what I'm writing. Y equals 4. And then sine opposite, square root of 9 minus x squared over 3. Okay. So I started by moving the 4 to the other side, so I got y divided by 4 equals the square root of 9 minus x squared over 3. Then I squared both sides of my equation to get rid of that square root, which gave me y squared over 16 equals 9 minus x squared over 9. I'm going to move that minus x squared to the other side, so I get x squared over 9 plus y squared over 16 equals 9 divided by 9 is 1. And we see that this is an ellipse. So since y is bigger with the number underneath, we know that it's going to be vertically. Okay, so when we go to graph this, my major axis, minor axis, okay, we found that, and again we're going to substitute 0 in, so an x cosine of 0, y equals 4 sine 0. This gives me x equals 3. This gives me y equals 0. So we start at 3, 0. That's my initial point. And then we go this way around. Okay. Okay. We're on to the next one. Example 4, draw and identify the graph of the parametric curve defined by x equals 3t, y equals 2 minus 2t. Okay, so x equals 3t, y equals 2 minus 2t. We're going from 0 to 1. Once again, we want to get that t by itself, so we have t equals x over 3. I can substitute it in here. Y equals 2 minus 2 times x over 3. Okay, so that gives me y equals negative 2x over 3 plus 2. So if we're going to graph this, we know it's a line with a y-intercept of 2. And then we go down 2 over 3, 1, 2, 3. Okay. So when x is, let's do t. So when t is 0, so x equals 3 times 0 is 0. And y equals 2 minus 2 times 0. We end up with 2. So our point that we start at is 0, 2. So this is my initial point this time. Okay. And then we know if we substitute in the 1, we'd have what? Let's start with x. Jenkins, x equals 3 times 1, which is 3. Y equals 2 minus 2 times 1, which is 0. So 3, 0 is my terminal point. See it going like this. And we're going to move along in this direction. Okay. Let's try that again. Find the parameterization for the line segment with endpoints -2, 1, and 3, 5. So I'm going to take a second and just graph that for me to see. Okay. Okay, so that's a rough graph what that's going to look like. So we want to use -2, 1 to recreate this. So what we're going to use is a x equals, and then what our x value is -2, and then the change in the x value is going to be a, and then some effective t. And then we have y equals, and the value there was 1, plus, and it's the same idea, some number b, the effect by the change of t. Now we're going to solve using our other point with this. So let's say when t equals 0, we know it goes through -2, 1. Okay? And when t is 1, it goes through (3, 5). Okay, so we see this works because if we put 0 in for t, we need to get the original point. And then now we're going to substitute in 1. So we end up with, let me change this. I always want to write in different colors. Okay, t -2 plus a, substitute 1 in, and we know that equals our x value of 3. And then for y, we have 1 plus b 1 equals my y value of 5. Okay, now we're going to solve for a and b. Okay, I'm going to add the 2 over. I get a equals 5, b equals 4. So I end up with spaces that I'm running out of. X equals -2 plus 5t. Substitute in what I have. Y equals 1 plus 4t. Okay. And then we know this is working from the parameters we set from 0 to 1. And box it in so I know that you're done. Okay guys, thanks for watching the video. Let me know if you have questions on the homework.